Hello my dear students, in the last class we have studied about online UPS, offline UPS, okay, and this is regarding chapter number 8. So as a last session of this UPS, applications of UPS, application of UPS, it is a power line. Today's topic is like this: applications of UPS, power line disturbances, sources and effects of power line disturbances, how to suppress these disturbances, AC voltage stabilizer, okay, CVT constant voltage transformer, and AC servo voltage stabilizer. So these are the contents of today's topic. Now coming to this, the first one, application of UPS. So it is used in computers, data processors, data transmitters, microwave relay stations, digital controllers, and nuclear reactor control systems. So these are only sample list, that's all. So even if you can write many more applications like this. So this is under applications of UPS. Now types of power line disturbances. Moving to this power line disturbances, it's a quite common feature in power system. And what are these disturbances and how do they affect, and what are the sources of errors, etc. So these are the important points that I am going to cover in today's session. So transients occur owing to switching surges and lightning surges in power line networks. You know, switching surge is a common phenomena, and lightning surge very rarely occurs during rainy season. These surges increase the instantaneous voltage in the positive negative half cycles. So this is a surge, that means the instantaneous voltage, it may last for 0.5 to 200 microsecond. You see the time period of this surge. This is called as a transient. So it occurs due to switching surges and lightning surges. So this is the first power line disturbance, that is transients. The next one is electromagnetic or radio frequency interference. So how do they occur? Switching and lightning surges and ignition systems of automobile can introduce these electromagnetic and radio frequency interference in the supply of AC lines. So this is the second disturbance, that is electromagnetic and radio frequency interference. Now coming to the next one, sudden overvoltage or undervoltage. So this is another phenomenon. So how do they occur? These are due to load variations. So load will vary. Suddenly the load is thrown on, thrown off, etc. This is one reason. And the other reason is your faults in the power line. Maybe there are several faults which may occur in a power system: single line to ground fault, line to line fault, three phase fault, okay, double line to ground fault. So there are many faults which may occur. So those faults will cause this sort of sudden overvoltage and undervoltage. That means load variation. Load variation is sudden throwing off and throwing on the load on the power system. This is another phenomenon. The duration of overvoltage or undervoltage may lie between 10 milliseconds to 2 seconds. So this is enough to cause damage. The occurrence of overvoltage may be due to spikes and surges. So what are these spikes? Spikes are very high voltages and are split second events that can disrupt operation of computers. This is a most important phenomena which can damage your computer systems. That is called as a spike. So once again, the cause of the spike is a lightning or switching on or off electrical loads, large electrical loads, capacitor loads, etc. So these will cause the spike. Next, surges are overvoltages that exist for more than one cycle and are caused when heavy electrical loads are suddenly switched off. This is a surge. Sag is called as an undervoltage that exists for more than one cycle. The sag and surges are another major phenomena to be addressed to. Then production of harmonic waves. Harmonic distortion is introduced in the supply line when non-linear loads, please note this point, non-linear loads, that is current is not exactly proportional to the applied voltage. So when this non-linearity occurs, when you switch on or put power controlled rectifiers or adjustable speed drives, you have studied many adjustable speed drives, that is VSI and CSI, voltage source inverter, current source inverters, converters for speed drives, etc. So these are common devices that we connect in the power system. Now when we use this kind of semiconductor devices for speed control of motors, which is quite common in industries, so this will cause the harmonic production. So these introduces non-linearity into the circuit. So we should take care of these drives and switching harmonic waves. Then one more phenomena, that is a constant voltage transformer produces a distortion as there is no input transformer preceding it. Of course, CVT is a power conditioner. In fact, in the short while from now I will be discussing about CVT also, but still CVT also produces some sort of distortion in the circuit. Such equipment produces high level of distorted input current, which develops distorted output voltage in the source impedance. This is important. Net output impedance becomes distorted, so it directly affects the impedance of the circuit. The upper limit of total harmonic distortion should not exceed 5%. So this is the limitation, which a requirement in fact for a CVT whenever you are using in the circuit. Now this is about one sort of distortion. Then another one is a sustained under voltage, means a continued under voltage. How it occurs? The voltage outage is the another type of outage, means switching off, sudden switching off of the system. That is, voltage outage is another disturbance which the supply voltage goes down below the allowable value. If the supply voltage goes below, this is called as a sag, we say. This voltage outage occurs owing to excessive and extreme variation in load, faults in the power system, malfunctioning of the equipment. All these things will cause sustained under voltage. This is another phenomenon. See, sustained under voltage, in other words, is also, in other words, it is a burnout, is the low voltage condition that can be present even for several hours. This is very important point to be noted. That is sustained under voltage. This condition is often created when the power demand exceeds the capacity of power generator. That means power demand is more, capacity of generator is less. Obviously, there will be a under voltage. So this phenomena is very quite common. You might have conducted experiments on alternator also, right? In your laboratory, you have conducted an experiment, load test on alternator, direct loading of alternator. In that case, you might have observed, as and when you load the machine, the load current decreases, voltage decreases. If you keep on increasing the load, it may further decrease. Of course, there are many aspects which comes into picture, but for discussion's sake, so sustained under voltage is due to the power demand exceeding the level, that is capacity of power generator. Now, single power generator has to cater the exceeded demand. So naturally the voltage will reduce. This is a sustained under voltage. So this causes severe disturbance in the power system and severe disturbance to the connected load, especially your computers. So they are very sensitive equipments. Then coming to the effects of power line disturbances on sensitive equipment. This is another unit in your syllabus, power line disturbances on sensitive electronic equipment. So, what does it affect? Number 1 is your transients. So, all these disturbances definitely causes some sort of failure of the equipment, and you have to take care of non-occurrence of these disturbances, of course. Number 1 is your transient. In the very beginning I started with transient. Transient causes errors in the results and damage the equipment if proper care is not taken. Transients are switching surges, that is all. It causes sudden increase in instantaneous voltage, which can definitely damage your ICs which are present. So, since your equipment being very sensitive to such voltage surges or transients, definitely it will cause a damage. The other one is your electromagnetic and radio interferences, which results in erroneous results of the sensitive equipment. This is electromagnetic and radio interference effect. The next one is the overvoltage, undervoltage conditions lead to errors in result, shut down or damage the sensitive equipment. All these things are quite common in feature which causes errors, introducing errors in the computer system, but they are being dealt separately here, that is all. So, what about spike? Spikes are very damaging and could burn the complete motherboard of the computer system. Of course, each and every component, they have their own way of disturbing your computer system. And of course, sag or undervoltage, continuous undervoltage. So, this causes slowing down of your computer disk, because they are designed for certain speed and certain voltage or certain current, and the motor inside, your stepper motor maybe. Okay. So, this causes the motor to run in a slower motion, then your computer disk drives, they will rotate at lower speed. Then when they rotate, you have a read head and write head, which are very sensitive devices for reading and writing. This leads to data errors definitely. This point should be very carefully understood. That means sag or under voltage causes this sort of crashing, head crash results in permanent loss of data. So, this is a sag. That means it is severe than your spike. Spike will occur only for a short period of time, so that you can take it for an account. But sag is a continuous or continued low voltage applied to the disk. This is quite dangerous. So, this should be avoided altogether. Now, you have harmonics. Harmonic waves affect the stability of stabilized power supply and malfunctioning. It is quite common. How harmonic affects? See, you have electronic controls depend on zero crossing or voltage peak for exercising power control. This concept we have discussed while discussing converters, okay, and inverters. Now, when you design your electronic control system, and you are going to use thyristors, so we use line commutation, and we have seen zero crossing of the wave. Okay. So, if the zero crossing of that wave is not happening as per your calculations, definitely it will introduce errors in the control system. The harmonics can significantly alter these parameters. So, this is a very important phenomena. You should not allow these harmonics to play with your system for your power supply. So, why? This is the reason. That means it disrupts the zero crossing of your original sine wave. So, when once you have designed your commutation circuits or whatever circuits for power control, so definitely there will be a shift of this zero crossing line. Now, the moment this zero crossing shifts, definitely there is a error in the system. Okay. So, this electronic control will not happen as you desired or as you have designed the system. And voltage outage, shuts off or damages the sensitive equipment. This is a common phenomenon. Definitely all these disturbances will contribute for its damage. So, this is an important thing. You can see here, this is a chopped voltage waveform and distorted voltage waveforms of your AC sine wave. You can see the different choppings and spikes which have been shown here. So, these are the spikes, and even more spike, you can write spike in a different manner also here. Okay. Now, this is a chopped voltage waveform along with the spikes, etc. This another graph, it is a distorted wave. Your zero crossing is disturbed here due to harmonics. Okay. See here, the original sine wave is disrupted, and original zero crossing is no longer true according to your 50 hertz, 20 milliseconds. The total time period from here to here is 20 milliseconds. It should be, if it is exact, 50 hertz. But due to harmonics, what is happening here? It has shifted its zero crossing line. Now, this is a simple indication. Of course, even you can write one AC sine wave like this, pure AC sine wave, distorted AC sine wave due to harmonics, chopped voltage waveform, and along with the spike like this. So, you can introduce the spike here, sag here. Of course, some voltage sags can also be shown here. Okay. So, this sort of voltage disruption occurs whenever we choose this disturbances. So, whenever we discuss about disturbance, so we have to see this. Once again, this listing is done here as a simple technique. In practice, voltages can significantly depart from ideal condition. That is, one is overvoltage. Overvoltage is voltage magnitude substantially higher than normal value of sustained period for a few cycles. Under voltage is also called as burnout, which I already been told you. Already been discussed here. Burnout is the voltage is substantially lower than normal value for a few cycles. Okay. So, this utility system will collapse for a few cycles or more. So, this is outage or blackout. Then these voltage spikes, these are superimposed on normal 50 hertz waveform and occur occasionally. This can be either of line mode or common mode type. So, this word, these are superimposed on normal 50 hertz waveforms and occur occasionally, not in a repetitive basis. That is a spike. It is an occasion. That means switching high voltage heavy loads on the system. So, this can be either of line mode or common mode type. Of course, these will not be discussed here. In fact, only the voltage spike and its effect has been discussed already. So, chopped voltage of waveform refers to repetitive chopping of voltage waveform and associated ringing. So, this is ringing of voltage waveform. Harmonics, once again, distorted voltage waveforms containing harmonic voltages components at harmonic frequencies exist in sustained basis, continuous basis. Harmonics are continuous. Electromagnetic interference refers to high frequency noise, okay, which can be conducted on power line radiated from its source. So, this is electromagnetic interference. Now, from where these disturbances, what is the origin of these disturbances? Of course, this is another question which will be asked. You have to list out the different types of disturbances, then the sources of disturbances. So, what is the source of disturbances? Say the sources that produce these disturbances are very diverse. They are very, very different. Diverse means different. Many types of components, different loading patterns, okay, different paralleling patterns will have different sources. They themselves are the different sources. The first one is sudden decrease in system load causes over voltage and utility voltage goes up. This is the one cause, source of disturbance. Suddenly if you decrease the load, this will cause, this is the one cause. The another one is under voltage may be caused by overload condition. So these 2 points should be very clearly understood. One is sudden decrease in system load causes over voltage. This is the cause for over voltage. You can see here, cause of over voltage is sudden decrease in the system load. This is the first one. Secondly, the under voltage may be caused by overload condition. Suddenly if the load keeps on increasing, it is not a surge, this is overloading. Overloading is in terms of percentage, 10%, 20%, 25% like this. So as and when you increase the load incrementally, so voltage will decrease. So this is the cause of under voltage. Then the other one is large voltage spikes. What is the source? Switching in or out power factor correction capacitors, capacitor banks. So these are very important devices in the power system. So capacitor banks are to be switched on to improve the power factor, because most of the loads in the power system are inductive in nature. So to improve the power factor, you have to switch on, or you have to put capacitor banks. So as and when power factor correction is needed, so you will be switching in and out these correction equipments. So this will cause the large voltage spike. So this is the source or cause of disturbance. So this you have to clearly write. Large voltage spikes, the cause is switching in or out power factor correction equipments. The next is the power lines or pumps and compressor motors nearby chopping of voltage waveform. Chopping of voltage waveform may be caused by AC to DC line frequency thyristor converters. This is another phenomena. This is the source. Whenever you connect this kind of thyristor converters, this kind of chopped voltage waveform is quite obvious. This we have seen in while discussing about the waveform techniques of thyristor converters. Okay. Converter is a device which converts AC to DC, inverter DC to AC. Okay. So whenever we use this kind of devices, the firing angle plays an important role, and then trapped or recovery voltage plays an important role. Commutation is also another important aspect. So you have to look into many aspects in this power line, pumps, compressor motor, speed controls, okay, thyristor converters. Whenever you connect, this causes chopped voltage waveform. So this is another source of disturbance. Number 5, voltage harmonics. These harmonics are caused due to variety of sources. There is a list of source. Magnetic saturation of power transformers. Now the connection of power transformer is quite obvious in a power system network. So when you connect, the transformer gets saturated. Okay. So this causes voltage harmonics by a variety of sources. There is a list like magnetic saturation of power transformers, harmonic currents injected by power electronic loads, harmonic currents. Okay. So the harmonics are introduced due to these devices like power transformers. Okay. And then you have power electronic loads. So these are the disturbances. Then electromagnetic interference is produced by most power electronic equipment due to rapid switching of voltage and current. We have studied about this rapid switching. All these power semiconductor devices, whatever you have studied, All these equipments are switching devices. They are mostly used as switches. Maybe your power diode, power mass FET, IGBT, GTOs or whatever it is. This causes your electromagnetic interference. So, these are the list of sources. Okay. Then what are the effects? Once again, we have already discussed about this effect of power line disturbances on sensitive equipment such as computer, right. Depends on following factors: type and magnitude of power disturbance. On what factors it depends? Type and magnitude, whether it is chopped wave, spike, sag or whatever it is. Type of equipment and how well it is designed, this is another factor. If any power conditioner is used, sustained over voltage, under voltage may cause equipment to trip out. It is highly undesirable. This is another effect. Though there is a power conditioner, if not designed properly, the equipment will trip out. Large voltage spikes may cause hardware failure of the equipment. This is particularly with respect to computers we are speaking now. Earlier it was with respect to power system load. Now this is with respect to computer power system. Protection is offered by incorporating surge arresters such as metal-oxide varistors as an input device. So, still spikes of large magnitude with higher frequency result in hardware failure, chopped voltage waveform, voltage harmonics, all these things are, if not designed to be, immerse such effects or reduce such effects. Power conditioners consisting of filters and isolation transformers can correct such problems. So, there is a solution also. The effect of power system outage depends on duration of outage and equipment design. So, for an outage of longer duration 100 milliseconds results in shutdown of the same time, it will shut down. It is unacceptable. So, it can be corrected by using UPS. This is the correction factor. Then what are power conditioners? They provide effective way to suppress these or some or all in fact, and gives constant voltage other than power outages, the frequency deviation from 50 Hz. So, this is fixed by these power conditioners. Without what we discussed, these are the interferences that you experience in a power system and effects on power system, effects on computer system. Now, how to fix this? To fix these problems, you have power conditioners. Okay. Now, what are these power conditioners? Metal-oxide varistors. So, this is another list you can give like this: power conditioner, its function, and what are the power conditioners. Metal-oxide varistors, protection against line mode voltage spikes. Electromagnetic interference, filters, helps to prevent chopped waveform and prevent equipment from conducting high frequency noise into the grid. So, this is how to prevent electromagnetic interference. Isolation transformers with electrostatic shields provide galvanic isolation and filters line mode and common mode voltage spikes. So, this is how to prevent the voltage spike we using isolation transformers. Ferro-resonant transformers provide voltage regulation and filtering. Ferro-resonant means we will be discussing it in CVTs. Ferro-resonant transformers, voltage spikes and partial common mode noise. Linear conditioners are used in many sensitive applications to supply clean power. Of course, clean power is order of the day. So, clean power technology is being worked out in many industries to give maximum protection to your computer system. Now comes your constant voltage transformer. Constant voltage transformer, you can see here, this is the circuit expected from you. So, this is a primary coil, secondary coil, iron core inductor, compensating coil and a capacitor, of course. So, what is a constant voltage transformer? Coming to the conventional power transformer, it has a primary and it has a secondary. If you plot a graph of flux versus magnetizing force, you can see the initial portion is quite linear here. Later on it is moving to saturation. since it has only one magnetic path, it happens. So, how to make or bring this transformer to saturation? Give it two parallel paths here like this. You have one parallel path and you have another parallel path. Okay. Now, we observe this waveform, it is stretched like this, flux versus magnetizing force. Okay. So, you can see in the linear portion the variation in flux produces small variation in primary voltage, produces large variation in flux. Okay. As and when it reaches saturation, okay, the variation in flux is very minimum. Now, it is reaching saturation here in this case. You can see the variation in voltage, primary voltage Vp1 to Vp2. The variation is not appreciable here. So, that is why you provide a shunt path, a resonant path. Of course, a capacitor is connected here for the resonance. You know what is resonance? Connecting inductor with a capacitor causes resonance. So, if you bring to resonance, it will go to saturation like this. Okay, this is the point where we catch upon, bank upon the CVTs. So, the basic principle of CVT is, it has been given in this figure, you know, how the conventional power transformer Vp, okay, this is a conventional power transformer Vp, changes in Vp, primary voltage, and how it is happening here. How conventional primary voltage sets up magnetizing current and flux, right. Whereas, the operating below the knee of this phi 1 to phi 2, the secondary voltage is proportional to primary voltage. Above the knee, it has a little effect. This description has been given here. That is what I have discussed now. The description about the primary voltage and the secondary voltage. The variations of this primary voltage and secondary voltage are given, are shown in the graph. From that graph and from this description, you can always understand what is happening here and what is happening here. So, the variation in flux is not appreciable here, variation in flux is not appreciable here, okay, in this saturation mode. This is the point where we want to increase the regulation of your transformer, okay. So, another important thing is they have a little effect on Vs, that is secondary voltage. Above the knee, that is what, above the knee, changes in primary voltage have a little effect on secondary voltage. Even if you increase Vp, Vs will not increase. This is what the regulation requirement. So, the magnetic shunt and a capacitor across the secondary, the capacitor current IC generates additional flux in the secondary leg through the shunt path. This is the point, that is resonant path. Now, the total flux in the secondary leg is now above the knee voltage, so that Vp will have a considerably reduced effect on the secondary. Now, the point is you are operating in the saturation region. So, to minimize changes of secondary voltage with respect to primary voltage, further a compensating winding can also be added. So, this has been shown in the earlier diagram, the compensating winding added over the primary winding and is connected in series opposition, this point to be underlined, in series with opposition to the secondary to subtract from Vs. So, we have shown this in this diagram. This is the one, secondary coil, primary coil, compensating coil and inductor. So, this is your inductor core with the capacitor, they are connected in series. So, this description is given here, okay. Okay. Now, this is the diagram. Now, this is connected in series opposition to the secondary to subtract from Vs. Now, we will see this. This is the diagram that you can write. This is also a very clear cut diagram, primary winding, secondary winding with a common core like this, compensating winding. You can see the dots, it in phase opposition. This is Vc and this is Vs, secondary voltage Vs. And this is the output voltage V0, a constant voltage that we require. So, load current is increased, the compensating winding bucks out less of secondary voltage. So, this will have a bucking effect. So the effect is drop in secondary voltage normally associated with increasing load. You can see here, this is the graph, you can easily understand here. So this is your V out, this is your secondary voltage Vs. You can see the locus of this voltage, load increasing in erratic manner. But what is its function? Vc, that is a capacitor voltage, resonant voltage. This is a vector, it is in opposition. So this is your Vs, secondary voltage is abnormally trying to increase, but your Vc decreases and keeps this locus constant. Any increase, you can see here Vs is trying to increase, trying to catch this, but Vc is reducing it because it is in phase opposition. Okay. Now this locus is maintained constant. This locus is maintained constant. Now your Vc plays an important role here, which is in phase opposition, so that your locus of output voltage is always constant. Like this your CVT works. Okay. The next is your servo controlled voltage stabilizer. Servo controlled stabilizer requires this type of buck boost transformer. So here I am only giving you buck boost operation of this transformer. You can see secondary coil, primary coil, unregulated AC in output. This is regulated AC output. Here you have an auto transformer, variac dimmer stat, we can say. This is tapping point for X, tapping point for Y. So this Y will vary from Y, from bottom to top, like this. What happens when it varies? The description is given here. The variac feeds power to buck boost transformer, bucks, white bucks. So this is a buck boost transformer. Buck is opposition voltage in polarity. You know, you have conducted polarity test on transformer in your second year. Just now I think you have your laboratory, you have conducted polarity test on transformers. You know how to say how polarity changes brings you voltage 0 or opposition voltage. So when you reverse the voltage polarity, the voltage doubles, right? So you know the concept of bucking and boosting, you can understand there only from while conducting polarity test on your transformer. Now the amount of buck or boost depends on value of applied voltage to primary of your buck boost transformer. So this is the primary of your buck boost transformer. So this is the voltage which governs the buck boost operation of your transformer. Okay. Now how it changes? The output voltage depends on position of the wiper arm with respect to tap X. So tap X is shown there. If the wiper is set to tap Y, buck operation. Bucking means reducing the voltage. If the wiper moves towards tap X, the primary voltage becomes lower and lower and it leads to boosting operation. As and when you vary the tap Y towards X, so it gives you boosting operation. As and when you vary it down, it gives you bucking operation. So based on that you have this servo controlled stabilizer. So this is your buck boost transformer. Okay. So buck boost transformer concept has been explained just now. So this is your variac. Okay. So now this block diagram you have to write. This is the sensor circuit which senses the variation in voltage. Okay. So this sensor circuit produces an error detector and amplifier. So if there is any amplification required, you can amplify this and run the servo motor. So what is a servo motor? It can run in either direction, either positive or negative, based on the error detector voltage, whether plus or minus. So this servo motor in turn varies this arm up or down, clockwise or anti-clockwise, so that this voltage is buck or boosted, so that the output regulated output is constant. So this is the explanation expected from you, servo controlled voltage stabilizer. Now basically you have to explain the buck boost operation of this transformer. From the basic diagram whatever has been shown, you have to write down this one. Okay, the buck boost operation of the transformer, right. So you have this unregulated AC output, you have an auto transformer and this is the tapping X taken here, this is a primary coil, and tapping Y is a variable point. Okay. So, the voltage applied to the primary decides what to do. This is a bucking operation or boosting operation. Okay. So, based on this concept, whether you move this Y towards X or Y move towards down, the voltage at the output remains constant. That is correct in phase opposition. Once again, boosting and bucking is like this. Bucking is reducing the voltage, boosting is increasing the voltage. So, that operation is done by connecting the polarity test. So it is just like a polarity test. Okay, the voltage induced here will act in opposite direction and brings in a regulated output. So, this based on this concept, this diagram is to be explained. Okay. Now, this regulator, this is an auto transformer variac, right, connected to an arm, movable arm like this. It can move on this winding, right. So, this is the variac. Okay. Now, to drive this arm, you have a servo motor. Okay. To drive this servo motor, you need an error detector and amplifier. Okay. Now, the sensor circuit. So, now you have to analyze this circuit diagram from this end. Okay. The sensor circuit will sense the variation in voltage. So, the sensor output is always less. If it is less, you have to compare this with the standard one, error detector. So, standard voltage is given as an input here. It will detect the error based on the output of this sensor. Okay. And this sensor, sensor output is very less sometimes. So, for that reason you have to connect it to an amplifier, because you have to drive this servo motor. Okay. To drive this servo motor, you need a little amplification of the voltage. So, now the output of the sensor circuit is taken and it is amplified first, and any variation in the voltage is detected by the error detector. Now, the output of this amplifier, after detecting the error signal, your servo motor can run either in positive anti-clockwise or clockwise based on the error detector output. So, this servo motor will run either in clockwise direction or in anti-clockwise direction based on the input, right. This servo motor will run in that direction. Now, the bucking and boosting operation, here this is your buck boost transformer along with the winding. So, the basic concept of buck boost has already been explained. The same technology is used here, right. So, this is your auto transformer variac, variable winding. This is the tapping of X. In the earlier diagram I have shown this one. So, next is your relay type voltage stabilizer. You can see there are two relays, relay number 1 and relay number 2, and here is your buck boost transformer operation. Along with you have a 3-point socket shown here. So, this relay will energize based on the bucking or boosting operation required. So, relays will have a NO and NC like this. Okay. They have NO and NC. Automatically when the relay is energized, then this NO or NC will trip and bucks or boost the output voltage. So, this is the circuit diagram expected from you, right, for a relay type voltage stabilizer. So, now this completes chapter number 8, which has been discussed, and now in the next class we will have switch mode converters. So DC converters, and this is all about chapter number 8 and probable questions. So you please refer specific instructional objectives in which you can always answer those questions, and these are the answers. Okay. So regarding application of UPS, different types of UPS, and effects of list of power line disturbances, effects of power line disturbances. Okay. And then you have to explain about CVT, constant voltage transformer, concept of CVT, and then you have to explain voltage stabilizer circuit using this concept of CV. Okay. And then relay type voltage stabilizer. So these are the contents, and you have to explain accordingly. Thank you.